Physical quanta versus weird math. Karl Popper wrote Quantum Theory and the Schism in Physics. He didn't have to. The logic of physics is empirical. Two theories, A and B, though contradictory, are equally true if their experimental predictions are the same, as we shall see. Einstein complained the wave function does not provide a complete description of physical reality. Nevertheless, the two proponents had difficulty to identify the difference between the theories and failed. Bohr's wave function is a probability amplitude and is complete. I've always had difficulty in describing the electron as a point particle because it has a magnetic moment with length dimension to the power 3 and with an uncertainty which is an order of magnitude larger than Heisenberg's uncertain limit. Other differences are mentioned here. But the main point is that these two theories, despite their difference, produce very successful descriptions of experiments in atomic and particle physics. They come unstuck on the quasicrystal, and I use that to describe the quantum. I include with Bohr, Dirac. He believed in beauty, not falsifiability and truth. He follows Bohr, and I wonder if you can find an untrue theory to be beautiful. Back to basics. Consider Young's slit. A coherent beam strikes two slits and they produce an interference pattern. This is analyzed by Huygens wavelets, and if the beam is very weak, the signal is time resolved on a scintillating screen. After a long period, the scintillations approximate to the laser interference pattern. Now, what happens to a single electron or photon passing through B? Is it going to produce this pattern or this pattern? Einstein objected that it has to know whether A is open or closed. And this requires spooky action at a distance, which was unsatisfactory. Well, we have a different kind of solution, and we'll see that as we go along. First, what is a quantum? In math, it's just an easy integer. In physics, it explains line spectra from atoms, Schrödinger's eigenvalues, blackbody, radiation, natural series, Bragg diffraction and crystals, etc., etc. However, it is easier to recognize the quantum in momentum transfers, especially in quasicrystals. I break the following outline into three: the probe, second phase crystals, and quasicrystals, and this into 6 subdivisions: diffraction, structure, and quasi-structure factors, analysis, quasi-block waves, and verification. I end with a hypothesis. Back to basics with 19th century physics, wave-particle duality. We include Maxwell's equations and Einstein's relativity. Add Planck's law, the Broglie relationship, and use simplified units. And we end with a very simple formula. Rest mass squared is equal to angular frequency squared minus wave vector squared. And this divides into 2 functions: a conservative function for mass, charge, spin, energy, momentum, and a resonant function for interference, superposition, creation, annihilation. For a free particle, it can be written in this expression, where the conservative function is an envelope function and the response function is an infinite wave with unit amplitude for all x and t. Other properties of this equation are described in the reference. Well, back to diffraction. The wave vector of the incident probe is k. It scatters elastically, and the quantum momentum is given by Bragg's law. n lambda equals 2d sine theta. Here's d, the interplanar spacing. And n is equal to 0, 1, 2, 3, 4, 5, 6. In this instance, odd orders are suppressed by structure factors because half of the atoms scatter in antiphase. N is integral, periodic, and harmonic. The diffraction is very well understood as harmonies between the incident probe and the ordered atomic sites in the crystal. Quasicrystals are completely different. N equals 0, 1, tau, tau squared, tau cubed, tau to the fourth, tau is irrational. It's aperiodic, it's anharmonic. How in heaven and earth does it diffract? Red lines are first order, green lines are second order. In Bragg diffraction on the left, the difference in path length between the incoming and outgoing wave is lambda, and in second order, 2 lambda. The wavefront is a plane wave, a straight line. Quasicrystals are different. The interplanar spacing is not regular, it varies. And the wavefront is not straight, it's broken. So how does it diffract? Well, we can't analyze this by Bragg's law, it doesn't apply. But we can use the structure factor method. But first, the structure. In crystals, the point group symmetry of the diffraction pattern is the same as the point group symmetry of the crystal. The same in quasicrystals. In crystals, the diffraction pattern is ordered in linear order. In quasicrystals, it's in geometric order. Here are the stereogram of the icosahedral structure. The principal axes and normal to them, the diffraction planes, are indexed in 3 dimensions, geometrically and completely. The manifold is R4. Dimension should not be multiplied without necessity. The geometric diffraction requires the hierarchic structure. Here's the unit cell, manganese at the center, it's icosahedral. The manganese is surrounded by 12 aluminum atoms, closely packed. Notice that normal to the 5-fold axis is a circle of 5 atoms, 2 circles of 5 atoms. We'll see those again. And the unit cell is edge sharing. Here it is in a cluster. Notice that the unit edge width of the unit icosahedral unit cell stretches to tau squared in the icosahedral cluster, and in the supercluster tau to the power 4, tau to the power 6, etc. The structure is uniquely icosahedral, infinitely extensive, and uniquely ordered. Here's an image, due to Bessel and Peng, of a thin section. It's in reverse contrast. Here's manganese. Here's a unit cell. 10 unit cells on 2 circles form a cluster, and 5 clusters on 1 circle in this thin section form a supercluster. The simulation in reverse contrast is on the right. So we can't analyze this by Bragg diffraction, but we can analyze it by the structure factor because they're independent of theta, and the analysis is numeric. In a crystal, we project each atom site onto a selected plane normal, sum the cosine phases to get the structure factor. The quasicrystal has multiple interplanar spacings, so we include a coherence factor. We'll discover what this is and calculate the scattering angle later on. The quasicrystal also has does not have periodic spacing between unit cells, so we have to calculate not just the unit cell but the whole structure of selected order, and we use the stretching factor. And what is the result? The result is there's no Bragg diffraction. If there were Bragg diffraction, it would occur on the ordinate axis where CS equals 1, zilch. However, when we scan CS away from the Bragg condition, these 5 Bragg peaks pop up. It's a surprise, but they pop up. They pop up at the same divergence from the Bragg condition by an amount we call a metric. And that's a surprise. But the biggest surprise is that all the diffracted beams from all the diffraction patterns pop up at the same quasi-Bragg condition. We can analyze that. After we've had a quick look at the pattern for a supercluster order 6 with 100 million atoms and a resolving power of 10,000. You can prove by mathematical induction that this geometric series is equal to this Fibonacci series. Here it is 1 tau, 1 plus tau, 1 plus 2 tau, 2 plus 3 tau, 3 plus 5 tau. And this separates into a natural part and an irrational part. You can approximate the irrational part to a natural part by substituting for tau 3 halves. And if you subtract this from the irrational index, you get the irrational residue, which we use in a metric function. And the extraordinary property is that this function is the exact inverse of the numeric metric that we derived before. The same for all values of m, even though this is numeric and this is analytic. We can now illustrate. Look at the blue wave. This is the block wave of a crystal at a Bragg condition. It's commensurate with the unit cell and with all unit cells periodically repeating, but incommensurate with the geometric quasi-lattice. However, if we stretch the block wave by the metric function, we find a quasi-Bragg wave which is commensurate long range at all intercepts and short range about each intercept. We have all the properties we need for sharp diffraction. And we can start making measurements. 40 years ago, several of us measured the lattice parameter based on standard methods and Bragg's law. I knew this must be wrong, but it took me some time to correct, and the answer is important, 0.29 nanometers. The lattice parameter is equal to the diameter of aluminum. This is an interesting cross-section. The icosahedral has 30 sides and 15 cross-sections identical to this. So the icosahedra are quasi-spherical. The hierarchy is of densely packed edge-sharing shares. Edge-sharing in inverted commas. So we can sum up. The quasicrystal metric harmonizes the irrational space and digitizes the resonant response with dual harmonies. And we can define the quantum. It is localized conserved properties on a harmonic response function. And we can make a hypothesis. Dynamic quanta are always harmonic. Math quanta are bare numbers with ugly corners, and I name a few. Physical quanta are beautiful when verified. There's nothing weird. They include wave mechanics.